the stream manager up. This is what I see. As always, if you're joining in, say hi, ask a question, whatever you like, and we will get into it. Today we're building some course materials. So I need to check to see if I'm live. Copy this. Yes, we are on. Oh, I need to edit stream info. Lockdown stream. This is actually part 2. That'll do. Updated. Now just share it to the different locations. Discord. Apparently Microsoft wants to buy Discord. That'd be a big play. Where do I want to share it as well? Oh yeah. Yeah. So it's 12 p.m. We've got a fair bit of code to write today. Or actually, it's more sort of a code review. I'm going to put this out on Twitch. And we've got to put a little bit of emojis. Boom. All right. Let's get it started. Let's get it rolling. Collab. I've got some code ready for this already. 09, Skimlet, NLP Milestone Project 2. So this is what we're doing. Clean up Notebook 09, Skimlet. So yesterday we wrote some code over here. GitHub. Oh, Gitu. So yesterday we worked on number 8, which is down here, of the TensorFlow course GitHub. NLP, TensorFlow NLP fundamentals. Still have to add the extra curriculum. Now we're up to working on the second last notebook of the course. How exciting. Milestone Project 2, Skimlet. I need to add some emojis. So by the end of this stream, we're going to have this notebook linked here, which is also here. I spent a fair bit of time creating this. We're replicating a paper, which is the deep learning model behind a 2017 paper, PubMed 200K RCT. Can I go to this link? Yes, I can. Here we go. We present PubMed 200K RCT, a new data set based on PubMed for sequential sentence classification. So the idea here is if you take an abstract, a medical or a randomized, that's what RCT stands for, by the way, randomized controlled trial. You take a paragraph of text and you want to classify each sentence. But the thing is sentences come in a sequential order. So like sentence 1, 2, 3, 4, 5, 6. So can you get those in order as well as classifying them to the right topic? So that's what we're going to be working on here. And it's an NLP project. So in the previous notebook, we went through some fundamental natural language processing concepts. The main ones being tokenization and creating embedding. So this is one of the very important points as well, is that once you start to work with machine learning, is that your way of not only getting the data, but your way of representing the data is very important. So in our case, we represent words by tokenizing them and then creating an embedding. Tokenizing could mean mapping, say, each letter to a single number, but then embeddings creates a vector, which is not necessarily we can understand what an embedding is, but a computer understands it very well. So in this project, we're going to be putting what we learned in the previous notebook, which is number 8, into practice. We're going to be building our biggest model yet. The goal of the dataset was to explore the ability for NLP models to classify sentences which appear in a sequential order. Yes. So this is the input. For example, can we train an NLP model which takes the following input? The following sample has had all numerical symbols replaced with @ So to investigate the efficacy of X, so this is a medical abstract, right? But see how these are all different sentences? If you just look at that block of text as it is, like you just look at this block of text, it's pretty hard to read. But if we were to break this down into line by line, objective, to investigate this. Methods, we did this. Results, we did this. Low dose, oral, that word. So these are medical abstracts, right? So, problem in a sentence, the number of RCT papers released is continuing to increase. Those without structured abstracts can be hard to read. So this is what we're trying to do. We're trying to create a model that allows us to skim literature, hence skim lit. So rather than just be faced with a wall of text, we want to break each of these down into their specific sentence and understand what each of them does. Without structured abstracts can be hard to read and in turn slow down researchers moving through the literature. So solution in a sentence, create an NLP model to classify abstract sentences into the role they play, e.g. objective, methods, results, to enable researchers to skim through the literature. Hence, skim lit. Yeah, baby. Before going through the code of this notebook, you might want to get a background of what we're going to be doing. To do so, spend an hour or two going through the following papers and then return to this notebook. So this is where our data came from, is PubMed 200K RCT. And this is the model we're going to be replicating. So this is actually from December 2016, but that's okay. There are models that have probably performed better than the model we're using right now, but what we're practicing is replicating something from a paper using the TensorFlow functional API. So neural networks for joint sentence classification in medical paper abstracts. This is what we're going to be replicating. Right? So we want to be able to take what a model looks like in a paper like this. So we've got character embeddings, we've got token embeddings. We have a bi-directional LSTM, we concatenate that. Then we concatenate the token embeddings and the character embeddings together. And then we put them into a bidirectional LSTM, then a feed-forward network, and so on. So we want to see how we can replicate this with the functional API. Because you might read through this and go, wow, there's so much here. But how do you actually take a paper and replicate it? So let's see if we can do that. So what we're going to cover, I need to add a graphic. Skim lit before and after. Like dog vision. Yo, Sheik, what's going on? Jiro, yes. The course, the first 14 hours of the course is on YouTube. It's the exact same as what you'll find. Yo, Alex, what's going on? Jero, if you want a surprise, paying attention to your last comment, keep watching the TensorFlow YouTube video. Let's just jump right into this and start writing some code, making sure it runs. I've got a few little tricks I want to potentially incorporate into this model because I've learned a few things of how to speed up stuff. The beautiful thing about this is that the data set is available on GitHub. Oh, we've got a K80. That's disgusting. I don't want that GPU. I'm going to factory reset runtime and get another GPU. What was your struggle in the Discord, Alex? I'll check it out now. I haven't replied to anyone in the Discord yet. I've just because I want to do some coding first, and then I'll get to the Discord chat later. But I'm going to check it now. Far out. We share a lot of messages in here. Oh, you forgot one letter in an attribute. My friend, I have been there many of times. Okay, now we got a T4. Now we're talking, baby. Boom. So this data set actually comes in two parts, which is very good of the researchers to do. I just needed to rearrange the contents of my pants because they were getting stuck. So there's PubMed 200K RCT and there's PubMed 20K RCT, which 20K RCT is just basically 10% of the 200K. So what is an important point when we start with machine learning experiments? Start with a small amount of data. Start with a small amount, get something working, and then scale up. So we're going to start with PubMed RCT, dev text, test train. So we've got 3 text files. Beautiful. Looks like we've got 3 separate text files. Yes. So a dev set is often referred to, another name for a validation set. Get all data files. Yeah. We'll have a look at that later. Okay, now we've downloaded some text data. Do you think we're ready to model it? Wait, we've downloaded the data, but we haven't looked at it yet. What's the motto for getting familiar with any new data set? I'll give you a clue. The word begins with V and we say it 3 times. Vibe, vibe, vibe. Sort of. We're definitely going to get... we definitely got to feel the vibe of our data. Values, values, values. Right again, we want to see lots of values, but not quite what we're looking for. Visualize, visualize, visualize. Boom. That's it. To get familiar and understand how we have to prepare our data for our deep learning models, we've got to visualize it. We've got to visualize it. Let's just go this. Visualize it. Because our data is in the form of text files, let's write some code to reach each of the lines in a target file. Beautiful. Simple function. Reads the lines of a document. Get lines, file name. Reads file name, a text file, and returns the lines as text as a list. Args, file name, a string containing the target file path to read, returns. Wonderful. So, get lines is very simple. It just opens with a context editor, then returns the lines. So if we read the training data set, get lines is not defined. Of course it's not. You're exactly right, Ashik and Alex. Transfer learning is very, very experimental. A lot of machine learning is very experimental. Okay, so this is what we get when we read our text file, train text. So we get a string like this, and what we're trying to do is this is the ideal output. So given one of these without labels like this, can we take a medical abstract and provide objective methods, results, conclusions, labels to each sentence? And then, of course, have them returned in order. That is our trouble. Reading the lines from the training text file results in a list of strings containing different abstract samples, the sentences in a sample along with the role the sentence plays in the abstract. So this is the objective of a particular abstract or a particular study. To investigate the efficacy of all the numbers have been replaced by by the way, of weeks of daily low-dose oral prednisone in improving pain, mobility, and systemic low-grade inflammation in the short term, and whether the effect would be sustained at X weeks in older adults with moderate to severe knee osteoarthritis. So a full-blown study, and what we're trying to do is classify these. So if you imagine, if we go to PubMed, this is where you get studies, lots of studies on PubMed, and we want to find out something about nutrition. What's recent in nutrition? No, we want nutrition RCT, randomized controlled trial. So this is pretty recent. Nutrition psychiatry. Observational and interventional data to suggest diet quality may be a modifiable risk for mental illness. This is interesting to look at. So this is what we're going for. There we go. This is a perfect one. Nutrition psychiatry. Is this an RCT? RCT is randomized controlled trial. It is. So what we're trying to do, we can actually use this one as our test. So look at this block of text. This is very hard. Like if you were to come across this, there's a lot going on here. You'd have to read the whole thing to even understand what's happening. So what are we trying to do with skim lit? Mental illness, including depression, anxiety, and bipolar disorder, accounts for a significant portion of global disability and poses a substantial social, economic, and health burden. Treatment is presently dominated by pharmacotherapy, such as antidepressants, and psychotherapy, such as cognitive behavior therapy. However, look, there's a lot going on here, but what we're going to try and do is we're going to take this abstract and we're going to break it apart. I'll show you another example. This is what we're building a model to do. PubMed. Let's get another nutrition study. Nutrition RCT. Maybe this one has been broken down. We'll go to the first one. Nope. We could definitely try that one as well, but I'm going to try this mental health one. Yes. Much easier. Purpose, recent findings. So let's find a different one. One that's been, this is actually very good because these are ones we could try to break down. Yeah. Okay. All of these are potential candidates for our skim-lit model. $1950. How do I get year? Let's go in the last 5 years. Role of personalized nutrition in chronic degenerative diseases. This is 2019. This is another one we could try. No, we need RCT. I'm just going to search here for RCT. What's a recent RCT? Randomized controlled trial. There we go. This is what we want. See the difference between these two? This is much easier to read. Look at this. Big wall of text. This broken down into paragraphs. So can we build a model to automatically do this? So in other words, separate this big wall of text into different things. Now you might not think, this might seem like a small problem, but imagine if you're a researcher and you have to read 100 of these studies a day. What if you went through this, if you had 100 of these that you were up against, it would be much more of a cognitive challenge to read through these than to go through something like this. Background, methods, I can see what they did. Yes, they're the methods. What were the results of this particular study? And what are their conclusions? Can we develop something like this for something like this? And you could imagine is then every abstract that gets uploaded to PubMed goes through our model, SkimLit, and breaks the abstract down into this. So if you wanted to find out about a certain thing and you had to read 50 papers in a day, well, you can skim it. You could go, what's the background? What's the methods? What's the results? What's the conclusion? So that's what we're trying to build. We're trying to go from this to this. And these are two great examples. So I'm going to copy these. Want this from, no, sorry. Turn this into this. Okay, does that make sense? We making sense? This is what we're building for SkimLit. Let's go back to our code. We'll get SkimLit over here. So this is what we're trying to do. We're trying to make this one on the right here. I want to make this look much better. So see here how this is broken down? Can we build a model to do that for this type of text? Okay, first we need to pre-process the data, of course. Yo, Renuga, what's happening? Ranjaju, the Discord is available for students of Zero to Mastery. So if you sign up for any of the Zero to Mastery courses, you'll find me in the machine learning channel. Renuga, today is April Fool's Day for me, and I'm quitting machine learning. April Fools. Knowing this, it looks like we've got a couple of steps to get our samples ready to pass as training data to our future machine learning model. Let's write a function to do the following steps. We need to take a target file of abstract samples, read the lines in the target file. For each line in the target file, if the line begins with the hash mark, it is an abstract ID and the beginning of a new abstract. Keep count of the number of lines in a sample. If the line begins with a new line mark, mark it as the end of an abstract sample. Keep count of the total lines in a sample. Yes, this is... So we actually have to build a pretty advanced pre-processing function here. Return all of the lines in a target text file. Where was that? Return all of the lines in a target text file as a list of dictionaries. We want it as a list of dictionaries because that's a good data structure that we can work with our model. Containing the key value pairs, line number, the position of the line in the abstract, e.g. 3. Target, the role of the line in the abstract, e.g. objective. Text, the text of a line in an abstract, yes. Total lines, the total lines in an abstract sample, e.g. 14. I might put in here, e.g. 14. This is actually a really fun project. Abstract IDs and new lines should be omitted from the returned preprocessed data. So, example return preprocessed data. This is what it looks like. A line number, 0, target, objective, and here's the sentence. To investigate the efficacy of X weeks of daily low dose. So this would be one element in our data sample. So we've got a function here, preprocessed text with line numbers, returns a list of dictionaries of abstract line data, takes in file name, reads in its contents, and sorts through each line, extracting things like the target label, the text of the sentence, how many sentences are in the current abstract, and what sentence number the target line is. File name, a string of the target text file to read and extract line data from, returns. So input lines uses our get all lines from file name, empty abstract, create an empty list of abstracts. Okay, and then we got just some for loops. It's going to go through. What this basically does is goes through each line in a sample like this and passes it so that it becomes a structured data form. Because right now these are just lines of strings, but we're gonna turn these into dictionaries. So that's what we do. That's what we do with this code here. I've already written all of this, by the way, so we're just going through to make sure that it works. How does it go? So the training samples, we have 180,000 lines. We have 30,000 validation and 30,000 test. And this is what it looks like after we've passed a single sample, right? So each line is now a dictionary. So we have a list of dictionaries. So we have line number 0, objective, line number 1, methods, line number 2, methods. It's 0 index, by the way, and this total lines is 11 for the first abstract, and then 10. So see how here, line number 0, it starts a new abstract. We have background, and then emotional. Emotional eating is associated with overeating and the development of obesity. Oh, don't emotionally eat, my friend. But are we starting with so there's 180,000 lines in our RCT 20K dataset, training dataset. Now the data dir we've set up start by using the 20K dataset. Yo, Sarone Daniel, what's happening, my friend? Greetings from Australia. It's great to see you. All the way from Colombia. Thanks for tuning in, my friend. Now, if we get the head of, there we go. This is an example. So this is, now we've structured our data, right? So we have the target, which is the objective, methods, results, and then we have the text belonging to that. Then we have the line number of what's in an abstract, and then we have the total lines of that abstract. Now you might be wondering, why is the line number and total lines important? Well, it's because we're trying to predict the sequence of how these things appear. So if you imagine, if you have an abstract like this, which is structured, it makes sense that the sentences come in a particular order. So it would be strange to have a background sentence at the very end. You're not going to tell someone the background of your study before you tell them the conclusions of that. Maybe in some world you might, but for the abstracts, how they're typically written is you start with a background or objective, you say what you did, you say the results you got, and then you conclude with the conclusions that you finished off with. So now let's see what our distribution is. So if we plot, now I might turn that into a histogram, shouldn't I? That'd probably be a better option. Plot, hist. No, that doesn't work. Value counts. So you can quite clearly see that there's far more methods and results sentences than there is background or objective. So it's a relatively, it's an imbalanced data set, yes. However, the imbalance is not extremely massive. We do have, well, it's almost an order of magnitude from methods to objective. So there's about 5x. So what's that? 59 divided by 13. It's about 5x more methods and results sentences than objectives. So we can do that. We could do that. How do we do that in the optimizer? Oh no, it's a loss function. TensorFlow weighted categorical cross entropy. Here we go. Sample weight. Here we go. Acts as a coefficient for loss. If a scalar is provided, so TensorFlow imbalanced multi-class classification. Let's see what the docs say for this. Jero, greetings from Australia. There we go. Yeah, so this is a massive imbalance. So I don't think we'll have too much trouble with imbalances. So this is for this case, it's binary classification, I believe. Really wish I could see the whole. Why can't I see this? Is that not scrolling? So where? Oh, that's cool to do the metrics. Yeah, so that's for binary classification. You got to be careful what models you use. What metrics you're using. If you have imbalanced data. Class weights, here we go, this is what we want. Yeah. So this is where you could use different class weights for an imbalanced problem. Notice how class 0, which has far more examples than class 1, has a far lower weight than class 1. You can put the class weights down here. what does this end up as? Is it better? Oh. See, is it better for fraudulent transactions to have false positives or false negatives? Yeah, that's something that could be an extension to this project, I reckon. Let's go over to here. So this is the lengths of the total lines. How many lines are in each of our abstracts? Let's get out of this. So if you imagine how a line is just one of these, so it looks like the most frequent is about 10 lines long. So how many is this? 1, 2, 3, 4, 5. So you would say this is about 10 lines long as well. So it would fit in there. So you've got some that are 25 lines long, but you've got others that are only 5 lines long. So most of the abstracts are about 7, about here, to 15 sentences in length. So it's good to check these things out to make sure when we do train a model or test it on unseen samples, our results aren't outlandish. Yes, that is true. Get lists of sentences. When we build our deep learning model, one of its main inputs will be a list of strings or lines from an abstract. We can easily get these easily from our data using the toList method on our text columns. So I think we should work on pre-processing the data. Since the labels need to be in numerical format, we use scikit-learn's label encoder to encode them into integers. So yeah, let's see, can we make our data loaders? That's what we want to work on. Holy crap. That's a lot of COVID. I think that's more than our... Well, we just had a lockdown here for 3 days. But I think it's stopping today. Australia doesn't have as many people as other countries in the world. All right, we separated our text samples, and as you might have guessed, we'll have to write code to convert the text to numbers before we can use it with our machine learning models. Yes, we do. So label encoder. Now, we could probably... How could we... Train labels encoded. Train sentences. So I wonder if we can... Where we can input some pre-processing here. Now I think this is another function we can take from our last notebook and put it into... Okay, we've got a function for evaluating our models. Now the baseline here goes pretty well. 72% accuracy will be the number to beat with our deeper models. And this is the baseline, which is just can I get rid of that? Yes, there we go. Which is just a TF, IDF vectorizer and a multinomial naive Bayes model, which is a good, if for text problems, you want to probably use multinomial naive Bayes for almost just a quick baseline. It works really fast. We've got a working baseline to try and improve upon. We've got to create vectorization and embedding layers. Yes, the vectorization layer will convert our text to numbers, and the embedding layer will capture relationships between those numbers. Yes. Since we'll be turning our sentences into numbers, it's a good idea to figure out how many words are in each sentence. When our model goes through our sentences, it works best when they're all the same length. For example, if one sentence is 8 words long and the other is 29 words long, we want to pad the 8-word sentence with zeros so it ends up being the same length as 29-word sentence. Yeah, that'll be important for batching. We want everything to be the same length. This is important for creating batches of the same size tenses. So the average length of a sentence is about 26 tokens. What's the distribution of sentence lengths? Yeah, so the majority are falling between 0 to 50 words. Vast majority. So it looks like the vast majority of sentences between 0 and 50 tokens in length. We can use NumPy's percentile to find the value, which covers 95% of the sentence lengths. So that means if we pick a value out of these, what value covers 95% of all of the data? And we found out that that's 55. 55, a length of 55. Have a length of 55 or less. Now, yes, we split it. Why is a sentence 55? Tokens in length. Yeah. Tokens in length. $55 tokens. So we want a max tokens of 68,000. That's the number of total words in the unique words in the vocabulary. So the max tokens in the vocabulary. So what are all the words, the different words that appear in this? So heaps, potential, that's 1, 2, 3, etc., etc. So we found from the paper, section 3.2, dataset split. The dataset contains 195,000 abstracts, yada yada yada, and it has a vocabulary size. V denotes the vocabulary size. Let's have a look in here. V denotes the vocabulary size is 68K. Beautiful. Oh yeah. I'm glad you guys are excited about or seeing this and being excited about what NLP could be used for. So you never know, there's text everywhere, right? But this is a legitimate problem. What if you were trying to read 100 of these a day? You would be burnt out. So if you could break them down into this, they're much easier to read. Imagine a Chrome extension that could just turn any abstract into a broken down. This could be a Chrome extension. Skimlit could be a Chrome extension. You could come to this, PubMed, and be like, hey, I'm a researcher. I'm going to break this abstract into something like this. This is what we're going for, right? That's what we want to build Skimlit to do. Of course, you need to build some like pre-processing functions around this, but let's have a look at this. Let's go to Chrome. How do we inspect? Inspect. Look at this. So this is just a paragraph of text. Look at this. Class, abstract. Abstract contact selected. Look at that. We just got the text from the abstract. We could take this, our Chrome extension, this is deploying it. This is full scale ML. Once we had a model build, we could just take this text and then restructure it to be in this format. Now, if we have a look at this, inspect, look at this, abstract, right? But there's another paragraph here, subtitle, background, boom, right? So this is what our model could be capable of doing. Once we have a model to just ingest text like this, and it can break it down at a pretty good rate, then we can reformat a user's website to something like this. That's a Chrome extension right there. Skimlit. Skimlit, baby. All right, let's keep building. But now you're starting to see where the idea is from. Let me just go, how do I get out of this? Right? Powerful stuff. There's hidden uses for this sort of technology everywhere. Let's finish off building the model. Of course, you want the model to work in the browser, so you could just replicate it with TensorFlow JS. The steps around this will be important first. PubMed should hire us, and we can create that Skimlit for them. Imagine how many researchers go on PubMed every day and have to read through this. Even I look at this and I'm like, far out, there's too much going on. So let's check out our text vectorizer. So this is what happens. So the aims of this study were to compare the levels of oxidative stress in patients with dry eye and patients without dry eye, to evaluate the effects of treatment with preservative-free eye drops containing high hydrochloric or hyaluronic, I don't know what that word is, and vitamin B something on oxidative stress and dry eye symptoms. Wonderful. Now, if we have the length of the text is this, we vectorize it, we convert it into numbers. So it's padded a lot because we've set the max sequence length to be 290. So why didn't we set that there, 55? There we go. So 55. The purpose of this study was to investigate whether individualized, deliberate practice on a virtual reality VR simulator results in improved technical performance in the operating room. Imagine that. This is some real stuff right here. This is someone practicing on a VR headset. Beautiful. Cool, we've now got a way to turn our sequences into numbers. This is an important point. Anytime you're doing machine learning, just find a way to represent your data as numbers and then build a model. Most of the time, the models will be already built for you. What this course does is it just exposes you to the main ways that models get built. Using the get vocabulary method for our text vectorizer, we can find out new different tidbits about our text. So, number of words in the vocab, 64,841. Most common words is blank, so space, unknown, the, and of. Makes sense? Most uncommon words is AA induced, AAI group. So these are probably just typos or something like that. Wonderful. If we want to figure out configuration of our text vectorizer, we can use the get config method. Yeah, Alex, you're right. Safari's reader menu. A sheet. Great answer, my friend. Renuga, depends on what sort of data set you want to build. If you want to create your own custom data set. An embedding, yes. So an embedding is a richer numerical representation of our text. So right now the vectorizer just maps each word to a specific integer, but an embedding puts those integers into vector space. And an embedding can be learned. The purpose of this study was to investigate whether individualized deliberate practice, so yeah, here's the vectorization, so before embedding, sentence after embedding. So now we have a sentence that is embedded into vector space. And so what a model can do is, although these numbers might not mean much to us, it can start to learn and adjust these. So these become the weights of a layer. So this is an embedding layer, and these are the model's weights. And so once it goes through different sentences, it can learn to adjust these to what it needs to understand. Time to build a series of deep models and try to improve upon our baseline. So that's an important point as well. We've created a baseline. Now, subsequent models, we want to improve upon that baseline. So this is, we're just building a convolutional 1D. So convolutional 1D is we're dealing with sequences here, which is text. Vectorize the inputs. Token the text vectors. Or create the embedding. Because our embedding layer is called token embed. Could we use categorical cross entropy? Why do we want sparse categorical cross entropy? Because our labels are in integer form. But I kind of want categorical cross entropy now because it has a little feature that I want to use in this project now. Sparse categorical cross entropy, TensorFlow. I don't think this has it. It doesn't have label smoothing. So we need categorical cross entropy because it has label smoothing, which is a handy feature to have. Yeah. Oh, sample weight. Label smoothing. Okay, so maybe we go up here and we rechange. How does our model go? See here as well, I think we can set up faster data loaders. Or maybe that loads it itself. See, because the text vectorizer, this is where we might be running into a bottleneck with our model, is we're vectorizing it before it loads. So maybe we could pre-process the text first instead of making it part of a model. Let's go TensorFlow text. Oh, TF text. I'll be back in a second. Yeah, you're totally right, Ashik. It's all about the data. Andre Karpathy, yes, great talks, Alex. All of Andre Karpathy's talks are very good. Okay. Do either of these use TensorFlow text? Yes, that's what we want. We want something like this. Ah, beautiful. That's what we want. Magic. Oh, what's embedding? TF Keras layers. Mask 0. Oh, that's a great feature. Okay, so we've got a good setup here. Let's proceduralize this. What a word, proceduralize. My man. Okay, so we can turn our yeah, this is what we want to do. Okay, so I might actually rip this out into a new notebook. Draft 2. I want to see if this works. Ashik, how do you feel now? Okay, let's go to where we were, but this time I want to make a better data set. And I don't... Do I want the labels one hot? Yes, I do. Okay. I want one hot labels. So what are our labels right now? If I go TensorFlow, I can just do from sklearn dot one hot encoder Renuga. That is so great to hear. Thank you so much. All of Andre's videos are great. And there's also skin in the game. Works on Tesla Autopilot. So that's what I feel I need to do after I finish teaching this course. I've taught enough for the time being. So I need to put my skills to the test. What is happening here? Beautiful. That's what we want. Do we want... There we go. Okay. So my labels are now one hot, which is what I want. And I believe I can now go class names equals great. What attributes does one hot encoder get? Categories. Num classes equals one hot encoder. get the attributes of these. Okay. That shouldn't be one. There we go. Okay, we don't need this. So maybe scikit-learn multinomial MB needs labels. Damik, nice to meet you, my friend. What's happening? It sounds like you're doing the right things. There's no set path in this world, my friend. You just find people who inspire you. May or may not be me. It doesn't worry about me. Could be anyone. But I'm just reading what you're saying. Ashik, maybe I should make more cooking videos. But Whammy, what's going on, brother? I would just say, Damik, keep going with what you're doing. Find things that interest you, find people that interest you, and just see what you can make of it. There's no real answer. All right, my little brother is telling me to check my email. Wham, I'm checking my email. There's nothing here. You sure you emailed me something? I should make more cooking videos. I love cooking. And I'm a good cook. Okay, so apparently multinomial MB doesn't fit on one hot. So it needs to be label. Far out. Need to accept cookies on every website. It doesn't take one hot? Surely it takes one hot. Multinomial. Look at this, man. What is going on here? Just tell me. Okay. Thank you, Renuga. I believe I do need the... If I get labels encoded, they work. Okay, so I need to encode it for the baseline, but one hot for TensorFlow. That's right. Label encoder for baseline multinomial, one hot for TensorFlow. TensorFlow will work with non-one hot, but I want to use label smoothing. Wham, are you still here? Have I got an email yet? Okay, now let's use TensorFlow, and we're up to here. So this is going to be really good. Text vectorizer, okay. Now, they turn their trained data set, okay. I think this is what we can do. Map it to the... So they do it there. But I'm using the functional API. Am I just making this harder? Trying to think. Can I just get the first 20? So I actually don't want to shuffle there. Let's just see what happens. We'll try this, because the other code is there. So that's what we're here for. We're going to try... Oh yes, but do we need that? Programmer nerd, what's going on? I don't stream on live stream on YouTube because that'd potentially clog up the channel. Plus, I find Twitch is a lot smoother for live streaming. Okay. See you, Ranuga. Have a good day. Hasnain, thank you so much. I'm glad you enjoyed the deep learning course. Batch 32. Prefetch. So, I think. We want train data 20K. Let's see what happens if we just run this. See what happens here. What I'm trying to do is speed up the data loading as fast as possible. However, this is only fitting on the first 20,000 examples of training data. So this could error out actually. Here we go. Yeah, so this is only on... That's a good option. We just do 500 batches. I've got an idea. Only fit. This is what you want to... What we're doing here is we're just speeding up our modeling experiment. Otherwise, we're going to be waiting far too long. Okay, that's good. Because then we can validate on the whole. We can validate on the whole validation data set. Yeah, that looks good. TK equals you can search for TK. The combination of TK doesn't appear very often in actual words. So when you find a TK, you know you've left it there on purpose. That's what I use TK for. You'll see it a lot in, well, I use it a lot in my in a lot of my different works actually. If I'm writing code or if I'm writing a blog post or something like that, and I write like the first draft and I come back to it. Well, I'm going to come back to it. I search for the TKs. So if I went like this, TK, I've got all of these TKs that I want to come back and make sure that they're fixed before I publish this notebook, you know? Yeah, real helpful. Because then, you know, like if you come back and you're like, oh, okay, it's pretty good. But then you can come back and go, why did I put all these TKs here? Have I checked each of these sections to make sure that they're ready to go? Okay, that works good. Yeah, that's very quick. That's what we want. Now I put a TK here. Only use 10% of batches. Faster training time. Because what we're trying to do is speed up our experiments. So predict on what happens if I just copy this. Boom. Easy money, baby. Oh, this will be interesting. Schmock at a pancake. Now, the TensorFlow hub embedding layer might not be able to deal with what we want it to be able to deal with. But that's why we So what we're trying to do right now is speed up all of our data loaders, because if you can save some data loading, why shouldn't we do that? Sarone Daniel, all of the notebooks are on GitHub. Thank you, Ashik, for sharing it. This one will be on there at the end of the stream, just tidying up a few things. Colab Pro, yeah, USA. It's not in Australia, I don't think. Colab Pro. Yeah. Why not Australia? What did Australia do? Validation data. What error are we going to get here? Oh, it worked. Bellissimo. Evaluate on whole. So interesting, our convolutional 1D layer performs better than feature extraction. Oh, we need to do conv1D with character embeddings. This is going to be fun. Change collab into dark theme. I've never used collab with a dark theme. I like the look of the light theme. Getting a drink. Let's try dark. Turn on dark mode.
Okay, I turned on dark mode.
Dark mode is on. But see, the docs don't have dark mode. I think this hurts my eyes more than light mode. I use Pomodoros. I used some this morning, Ashik, but lately I've just been working on things that take longer than 25 minutes, so I just work on them until I need a break. Turn off dark mode.
Okay, I turned off dark mode.
See, that's much easier for me to read. So we want to create a character level embedding. What's happening here? Char embed. Oh, look at this functional model. Okay, yeah, this is where we're going to have to fix things. This is a hectic notebook. I think we can... Look at the model we end up building. Yeah, this is a multimodal model. Characters, tokens, and structured data. We end up replicating this model. Where is it? This one. But we even add something over here. But the main thing is that you can use the functional API to do such a thing very easily. Well, not very easily, it takes some practice. Look at this. Token inputs, line number inputs, total lines. Concatenate them. Now, we might have to do recurrent dropout. Because I think as well... Okay, let's start moving towards this. This will be on the GitHub at the end of this stream, by the way, because I'm happy with the code that it is, but I'm just doing some functional improvements. So we need to create a character embedding. Train chars, yes. So now we've got it into characters. How many characters cover 95% of the data? 290. Now we want to create a char level token vectorized instance. Now, TensorFlow char level embedding. How can we make this? Wait, where did they... Did they create a character embedding? No. Holy crap, that took a long time. They use tokenizer. This is great. Okay. Let's fix what we need to fix here. We could actually set it to Beautiful. Okay, so the character embeddings don't give as good a results as the token embeddings, but that's okay. Now we get into combining some stuff. So we're going to combine the pre-trained token embeddings plus character embeddings. Hybrid embedding layer. Combining two different inputs. Now, I believe what we'll be able to do here... Okay, so this is where we're going to have to get fancy with our inputs. So see the inputs here? Welcome back, Renuga. Now, if I wanted to combine two data sets, how do I do this? See what happens here? Character inputs, token inputs, character vectorization, char embedding. So I'm going to the inputs it took this is a very full-on notebook. I believe I might be able to now if we go to from tensor slices, I think we'll be able to do this. Yeah. We could do I have an idea. Train char token dataset. Combine chars and tokens equals TF data. Then we put in a tuple. Ho ho, daddy's home, man, daddy's home. Let's see if this works. This makes more sense, because then we don't have to worry about indexing so much. And we can prefetch. Then we want to do the same for the validation. Beautiful. Now, this took 40 seconds per epoch. Do we get any kind of speed up? Compile first, of course. But only received one input tensor. Maybe I can put this as a tuple. How does it zip together? That's what could work. You're completely right, Alex. Surf and turf pizza, baby, best of both worlds. So this is very slow, right? See here, 129 seconds per epoch. What I'm trying to do is speed this up. So let's. Yes. Yes, yes. That is how we do it, my friends. That is how we do it. Super fast. But then it errors for the validation. But look how much faster that was. Oh, it didn't tell us how long. Okay, let's fix the validation. It's all about pre-processing the data. You get the data pre-processed, you get faster computation. That's what we want. That's what we want, my friends. Faster computation. And then we zip it together. All about the data. I can't wait to work on my own project, and well, this is one of my own projects, but my own project outside of the course, and use everything I've learned so far. We're gonna make the fastest possible data loading you've ever seen before. You gotta squeeze the compute out of your GPUs. That's what you're learning in this course, how to squeeze the compute out of it. Okay? Watch this. Oh my goodness. Optimized compute. I'll show you what the unoptimized compute was in a second. But we just saved ourselves a whole bunch of time. Ashik, I keep getting you with the claps. I get excited when I get something to work, you know? Look how much faster the compute is now. And we're not using mixed precision. Now, have a go at this. Before, it was taking 129 seconds per epoch, and we've just sped it up 5x to 23 seconds per epoch. Look at that, we'll fit the same model again. Look at this. 23 seconds per epoch. Same amount of steps, except this uses sped up data flow. Yeah, 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 yeah. We just saved ourselves a bunch of time. Speed up your data sets, ladies and gentlemen. Very important. Look at this. Still going. Same data. Same data, just loaded differently. Watch, and I'll prove it to you with the evaluation. Same code, different loaded data set. We're going to have to wait for this to run. That took 100 seconds versus 23. 5x speed up. Oh, ML Fit, you're right. What should we do, squats or push-ups? I'm going to do squats. We'll do squats and push-ups. So we've got 3 epochs plus another 3 epochs. That's 15 push-ups and 15 squats. ML Fit, ladies and gentlemen. Oh, I'm a bit stiff. How many is that? 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. One for good luck. Now we're going push-ups. Wow, I'm burping a lot. Let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Woo! What channel can you come to get machine learning, live coding, and push-ups? We need more cooking and fitness videos, you're right. Introducing ML Fit. Oh, just need to pick my nose live on stream. I'll just show you, I could just cook some meals that I make. Introducing ML Fit. Cooking while our model trains. This is taking a long time. I'm going to go piss. Look at that. Look at that. So let me just compare. This took 100 seconds per epoch. Now, if we evaluate different created data sets, what happened here? None. What's going on here? Oh, I love ice cream. And I love cookies. Ah, this didn't validate. Ah, there we go. We've got some sort of error here. Okay, there we go. We're back in the game. That took 20 seconds versus... Do we get much of a speed up here? About the same time during evaluation. So the speed up is during training. Okay, that's what we want. Nope, we don't want to undo that. Delete that cell. Undo, delete cell. We can kill this, and we can kill this. Predict on val. Biryani. Let's have a look at that. Oh, that looks delicious. Chicken and rice. Chicken and rice, baby. Okay, we're well on the path here. Now, what did this say? Did my brother told me that he sent me an email. Did it appear in my junk? No. All right, not important. Okay. It seems like combining token embeddings and character embeddings gave our model a little performance boost. Yes, that's right. There's one piece of the puzzle we can add in. What if we engineered our own features into the model? Yes, this is important. This is a fun part. What if we took our own knowledge about the data and we have about the data... What if we took our own knowledge about the data and encoded it in a numerical way to give our model more information about our samples? The process of applying your own knowledge to build features as input to a model is called feature engineering. Yes. TK, maybe we put a slide here. Feature engineering. Can you think of something important about the sequences we're trying to classify? If you were to look at an abstract, would you expect the sentences to appear in random order? Or does it make sense if they were to appear sequentially? Jesus. Okay. Abstracts typically come in sequential order, such as... Of course, we can't engineer the sequence labels themselves into the training data. We don't have these at test time, but we can encode the order of a set of sequences in an abstract. For example, Sentence 1 of 10. This is where multimodal comes in, Alex. So see here. So when we created our pre-processing function, and read in a text file of abstracts, we counted the number of lines in an abstract as well as the number of each line itself. So doing this led to the line number and total lines columns of our data frames. So train data frame has the variable or the column line number. So this is where multimodal comes in. We have text, but we also have a structured piece of data here about our data. Now, of course, we can never engineer the labels into the training data, but we can extract more things from the training data. So if you think about it, if we're doing skim lit, we come back and look at a high level. We're doing skim lit, right? We see this abstract. We don't know what each of these sentences are. However, we do know the order that they came in. So this is sentence number 1. This is sentence number 2. This is sentence number 3. Sentence number 4. And so on. And then we might have 10 sentences all beginning. So adding context to our model is if we were to look at this sentence, this last one here. Continued research is now required to investigate the efficacy of intervention studies in large cohorts and within clinically relevant populations, particularly in patients with schizophrenia, bipolar, and anxiety disorders. Now, if someone said that sentence came at the end of an abstract, that would make sense. But if they said it came at the start, you'd be like, that doesn't really make sense. So now we're engineering the order of things into our model. Does that make sense? Whereas if we said this was the last sentence in an abstract, mental illness, including depression, anxiety, and bipolar disorder, accounts for a significant proportion of global disability and poses a substantial social, economic, and health burden. If we said that was the last sentence, you'd be like, okay, that's kind of a strange place to finish off at. It sounds more like an introduction to a problem. So that's what we're going to do now, is we're going to build a model and engineer in the line number and the total lines. And an important thing is that the engineered features need to be available at test time. So are these engineered features available at test time? Yes. We could read in this abstract, count the lines, and then save each line's position out of the total number of lines. So that's available at test time. That's a very important point. So create positional embeddings. Let's create them. We'll use... How many different line numbers are there? So we have... The majority of samples appears to have, 15. 15 covers the vast majority, 15 lines, because it really starts to tail off here. So there aren't very many samples with above 15 lines out of the total set. So if we check the line number column, we'll plot a histogram. Yeah, see 15 covers most of it. So looking at the distribution of line number, it looks like the majority of lines above 15 or less. So we can encode this using TensorFlow 1hot, TF1hot, to a depth of 15. And if we have a look, that's what it looks like. We get this matrix. Now, of course, we're going to turn this into an embedding. Beautiful. We can do the same with the total lines. So if we run total lines, we see the cutoff, if we go from 5 onwards, or 21, it starts to dramatically decline after that. So the vast majority have about 15 total lines. So let's have a look. About 20. Check the coverage. So if we want to cover 98% of samples, we have to use 20, which makes sense. Beautiful. Okay. So now we can create positional embedding tensors. Wonderful. We're now going to build a tribrid model. So we're going to combine character embeddings, token embeddings, and positional embeddings. So let's see what this looks like. We have a model for the token inputs. We have a model for the character inputs. We have a model for the line numbers inputs, which is a dense model here. We might change this to 32 because a general rule of thumb is that with anything to do with 256, anything to do with number of units in a layer, you kind of want to have a multiple of 8. These could all be hyperparameter tuned, but multiple of 8 seems to work really well. So this is actually, we're combining 4 models or 4 data inputs into one here. This is where we concatenate them all. If you see there. Concatenate, etc., etc. So now our model here takes 4 inputs. Line number model input, total line input, token input, character input. So this is multimodal. We have tokens, characters, and structured data. It's really much better visualized when you print out a model. So see, there's the output layer. We have input 1, input 2, input 3, input 4. And you could do the same here, like if you had images or another form of text or something like that, it would be building an individual pipeline for each one and then concatenating them, and then they all get combined within the output layer. Does that make sense? So we could put an image model here if we had images, and then concatenate it here, and then we would have an output layer, and then it would combine all of those features together. We may not understand what the concatenation comes to be, but that's the model's job, is to figure out all those concatenation things. All of the layers except our embedding layer are trainable. We want to make sure that it's categorical cross entropy. And here we go. We want to create training and validation data sets, all 4 kinds of inputs. So we're going to make train pos char token data equals tf data sets. Now we need to really pay attention here actually. Let's copy this cell just before we run it again. Now this took 41 seconds. Let's see if we can speed that up a little. Data from tensor slices. Rohan, what's going on, my friend? Yeah, you're right, Alex. We're building structure into our model with the tabular data. So I think you're following along, but just to reiterate, is that this is our data set. This is how the training data comes. Previously, we've only used the text. Now we're incorporating where that position is in the line. So, because that's what we're after, right? If we wanted to turn this abstract into something like this, background, methods, results, conclusions, we want to make sure that the sentences come in the right order. So we've encoded that, we've built a model. Now we got to see, the important point here is now we have to create a data set that has 4 types of inputs, because that's what our model wants. inputs line number, total line, token, chart, character. And where were we? Creating from tensor slices. So this is where we'll need the train line numbers one hot, and this has to be a tuple actually. And then we need train total lines one hot, and then we also need train. It's not train data set, is it? No, it's train sentences, and then train chars. Wonderful. And then train pos char token labels. So this is going to create a tuple of these 4 inputs, and then the labels are just a TF data. It's data set, isn't it? Data set from tensor slices. Data set. We're trying to speed up our data loaders as much as possible. From tensor slices, and this will be trained labels one hot. And now we go train pos char token data set equals tf data dot data set, and we're going to zip together the train positional character token data as well as the train pos char token labels. Now, does that need to be a tuple? Yes, it does. And then we can go train pos. We can speed it up here by turning it into batches. Data set equals train pos char token data set batch 32 prefetch tf data auto tune. And then if we have a look at this, train pos char token data set, what does that look like? Wonderful. So we've got 4 inputs here in this tuple. This will be the train line numbers. This will be the one hot encoded train total lines. This will be the training sentences. And then this will be the training characters. Beautiful. And then we can do the same for validation. Validation data set. We could actually functionize this probably. But I'm just writing it all out so we get practice writing this stuff. And this is actually really helpful for me to explain. Let me know if something doesn't make sense. And of course, there's actually probably way too many variables currently in this notebook, but it's a fairly large notebook. Oh, what's happened here? Ah. Yep, you're totally right, Alex. You're following along. What is going on? We've got a variable mismatch somewhere. data, labels. Oh. There we go. So this is our input data here, tuple, and this is our label. So now, this is the results we got. So, see, okay, without giving that away, let's put in this. So we need train, pos, char, token, data set. We want steps per epoch. We want to take about int 0.1 times len validation data. So we just got rid of a whole bunch of stuff by creating data sets here. Okay, so this should work. So this is our new fit function versus this. So let's see how this compares to our most recent model. Model for results. Is this what we're trying to beat? Let's see. This is text only, or sorry, this is text and characters. So token and model for.summary. This is what we're trying to beat. So token and character embeddings, and we got accuracy of 77%, and then F1 of that, and then precision, recall, etc. So let's see what happens here. Boom. See what happens when we upgrade our data sets, when we load them faster? This one had a time of 41 seconds per epoch. Let's see if we can beat it here. Yeah, you're right. Alex, you're totally right. It's hard to understand structure just from the sentences, so we're adding the structure in now. Hey, Lazy, thank you. I'm glad you enjoyed the tutorial. So we see a little bit of a speed up here. 41 seconds versus 35 seconds. And this is where the real speed up happens, is after subsequent epochs. 26 seconds versus 40 seconds, because we've created our data loaders to be very fast. And now we see an improvement in validation accuracy as well. Haha. So this is what we were trying to beat. Model 4 results. Let's move this down a few. So if we now get rid of this, we can predict on val, pos, chart, token data sets. Thank you for the follow, Gabri. I appreciate it. Boom. Look at that. So how cool is that, Alex? You'll be interested in that. Is that that's a +5% jump accuracy, as well as basically +5 in F1 precision and recall for just adding the positional embeddings. That's amazing. Let's compare all the results. So the tribrid performs the best by far. Now, of course, we could try a different way of embedding, but the tribrid approach outperforms all the other models by a significant amount. Can create the F1 score. As you see, the tribrid token char pos performs the best. I might change that to pos token char. Maybe that's a better way to do it. Pos char token. Yeah, that makes more sense. Char token. How cool is that? And a healthy improvement for data that was just sitting there, was just waiting for us. TK. That's the power of multimodal models. Is incorporating a feature that not 100% obvious, but is kind of laying in plain sight. So I'm going to save this to, I have to save it to my drive. Just have to mount Google Drive. And we also have to do some more push-ups. Yes, you sure can. You can do transfer learning on multimodal models. We actually use transfer learning in this, one of the models. So our multimodal model is actually a combination of 4 different models. So we have token model, which we use TensorFlow embedding layer. So we're using transfer learning on this model. But then this is all from scratch, these ones here. So this is the only model with transfer learning. But if you wanted to do a transfer learning on the whole thing, you'd need another model that's in a similar structure. But we've done transfer learning on the token inputs, which is the words themselves. So if we go down here, I need to do 15 push-ups because we train for 3 epochs. But then we want to run this. summary, and then we need to create a test data set.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
Winner, winner, chicken dinner. So we're going to create test data set. Beautiful. Loaded model works good. So we want to actually just get this data set. Change these all to test. ML fit, baby. So to test, of course, you have to test on the same type of input. As you trained on. So we're going to cancel that and go test pos. Now, of course, the test data set doesn't have labels, or does it? It does. Hey. Man, this is a dope notebook. Oh, I got an idea. Put a slide here. TK. Example input versus example ideal output. Messy abstract to clean abstract. And then we could have our examples here. So this is a clean. And this is a messy. Now, where were we? Beautiful. So this is just some formatting just to make our data more visual. Oh, you know what I wanted to do with our latest model? Was I wonder if label smoothing improves it. So let's copy this. and I'll put this here as well. No label smoothing. We need to change our loss function. So now we just have to rebuild this model and retrain it. What we did was we added label smoothing. So let's see how that goes. Data sets are going to remain the same. So we'll just copy this out. Label smoothing is actually quite a good regularization feature. May not work too much here because we're not overfitting too much. So results without label smoothing. And then, what time is it? Ooh, I need to start getting ready to go because... So, Alex, it's a great question. I'll show you label smoothing with an example. TF Keras, losses. Label smoothing is a regularization method, and regularization method basically means to prevent overfitting. So if we have a look at this, we've got a loss function here, label smoothing. So what can happen sometimes with a neural network is it gets very confident on one particular label. And what I mean by that is, where's label smoothing here? What I mean by that is that it gives, So let's go back to the notebook. I'll give you an actual example. This would be better. So we get it, when we make predictions with our model, we get a whole bunch of prediction probabilities. But what can happen is that some of the prediction probabilities, where's our table? This is probably a better way to do it. I want to give you an example so you can see. So some of them can be really high. So you see here, results is basically 1 because it's 996. Can you see that? So what label smoothing does is it takes a little bit of this prediction probability and gives it to the other classes. So this gave methods a really high prediction probability, but if we turn on label smoothing, it'll give a little bit of this 0.99 to results and objectives. So maybe this will only be 0.95 by the end because results gets a little bit, objective gets a little bit, background gets a little bit, etc. Now, what that does is it makes the loss function consider other labels for this particular sample. Now, then because it's considering other potential labels rather than just being so stuck on this one label, because it's almost 1.0, because it's giving values, small values to other labels, it in turn ideally learns better weights that can be used for data that is unseen. So for example, if this is the training data and it gets so narrowed in at one particular sample, it stops learning. It stops learning for samples that it hasn't seen because it's like, I'm so confident on this one example that I'm not going to even give value to other potential labels. And so in a training setting, if it gets too overconfident on method, it may just stop learning values for results or objectives. So that's why label smoothing kind of hard codes that in. It's like, hey, at all times, give a little bit of value to other potential classes. So don't get so tunnel vision on one thing. give some value to other labels as well. And hopefully that leads to better generalization, because your model, although it still may give a fairly high value to methods, such as 0.95, because the other 0.04 has been dedicated to other labels, it'll still be a good model. However, it will generalize to unseen data a bit more, in theory, because it's given small values to other labels instead of being tunnel vision on one label. That's how I understand label smoothing. In a verbal approach, you could probably look it up a bit more in a mathematical approach. I think Pi Image Search have a great blog post on it. Pi Image Search label smoothing. Here we go, label smoothing with Keras. The beautiful thing is now that it's built into our loss function. Yeah, so previously, here we go, this is a good idea. This is a good example. So previously, you'd have this number 7, and your model may output something like this. Like, it's really confident that it's going to be a 7. So 0, 1, 2, 3, 4, 5, 6, 7. All right, 1.0 prediction probability. However, when you apply label smoothing, you give some of the values from the confidence of label 7 to the other labels. So that's soft label assignment. And then when you do that, your model seems to generalize better. So yeah, the answer is that we don't want our model to become too confident in its predictions. So I'll send this to you. But in that blog post, they craft like a custom function to do it, which you can do. But now TensorFlow, if you're using categorical cross entropy, has it built in automatically. So we can just apply label smoothing. So I hope that makes sense. Now let's see, this is without label smoothing, and we're going to add label smoothing. We've just reset our model, so it shouldn't have any weights pre-example. And we'll find out to see if label smoothing also improves our model down here. But again, it may not be too much of a dramatic effect because our model is not overfitting. By that I mean the validation accuracy is still higher than the training accuracy. So in fact, we may be over-regularizing our model, which means we could remove something like dropout up here. Dropout. But this is good. So see, the validation loss is higher. That's actually a good thing since we've turned on label smoothing, because that means we've got more room to move and to reduce that loss. Yeah, you're right. The higher parameter given to label smoothing, the more it gives to other classes. So we use label smoothing of 0.2, means that we'll use a value of 0.1 for label 0 and 0.9 for label 1. Okay, so we get basically the same results. It doesn't improve it too much, but the loss is higher, which means we have more room for improvement. Does that make sense? Because we've added label smoothing, we've got a higher loss. That means we could potentially increase our model to make it a more complex model and reduce the loss even further. So we'll go here. I would say it would probably help more on a larger model. Our model is fairly large, but still we could go bigger. And by going bigger, I mean increasing the number of layers, increasing the number of hidden units, etc., etc. So we could upgrade this. Upgrade these, 32, 32, 128. Okay, so we get a slight boost with label smoothing. Slight boost, 0.3%, but that's still pretty good, hey? Look at that. So we get about 0.4, actually. 0.4%, that's not bad, I'll take that for free, basically. And if we look into Resnet, this is actually a really good paper. Resnet Revisited. Where's the paper? Archive. So I got this from this paper. You might want to have a look. It brought in a bunch of different training upgrades. This is actually a spoiler alert for ML Monthly that's coming up. So I've included this paper, Revisiting Resnets, Improving Training and Scaling Strategies. So they actually found that by just doing a few training tweaks, they can get a fairly significant improvement on 1.7 to 2.7 times on TPUs. This is faster, right? So same results, but faster training, and 2.1x to 3.3x on GPUs. So that's amazing. Now, if we go down here, one of the methods that they used, here, label smoothing, got them 1.3% improvement in accuracy. That's amazing. Regularization methods. So some cool things there. Decrease weight decay, that's another big one. That's something we could look into later, but without going too far into it, this is a cool paper. I like how they broke down what they used to improve, or how they got their improvements. So the training methods are in purple, the regularization methods, so preventing overfitting, are in green, and the architecture improvements are in the yellow there. So if we come here, label smoothing seems to give us a little bit of a bump, which is great. Nothing too dramatic, but enough. Where were we? We're down here. Find most wrong. Yeah, so this is where it may help us the most, is with our predictions that were most wrong. So if we have a look at these predictions here, let's save the output for that, because now our model is trained with label smoothing. Let's see what happens here. Okay. So we still get some fairly high prediction probabilities, but they're wrong. That's fine. But then we can start to explore some of the mislabeled examples. So let's go from 0 to 10. So here's where we can manually inspect to see where our model has gone wrong and how does that compare to what we would think. So the target was methods in our case, and the prediction was results, and it had a very high prediction probability. And it was line number 9 out of 12. Okay, so there's some context. So in the saffron group, there was no decline in maximum isometric and isotonic forces after eccentric exercise, but a significant decline in the isometric force was observed in the control group. So our model is predicting results, but the target was methods. So for me, that's kind of, I'm going to side with the model here, even though I'm kind of biased because I trained the model. But in the saffron group, there was no decline in maximum isometric and isotonic forces after eccentric exercise. So that's kind of telling me that what they found, there was no decline. There was. The key word here is was, no decline. but a significant decline in the isometric force was observed in the control group. So that's kind of telling me a result there. Interesting. So I would side with the model on that one. You guys can tell me what you'd pick. This is again, targets was, we'll put a new line after this. This was again, target was methods, and the prediction was results with a very high prediction probability, and it was line number 6 out of 9 lines. So the text, the at is a number, by the way, negative something percent versus fish, negative something percent versus fish plus S something, but there was no significant difference between groups. So again, that sort of, that line there, that stands out to me as results. So I can understand why the model predicted results there, but there was no significant differences between groups. That's not a method to me. That's saying we found there was no significant differences between groups. A method would be, what did you do to test that there was no significant difference. Oh, here's a different one. This is the reverse. So the target was results, but the prediction was methods, and the probability was very high again. The line number was 3 out of total lines, 13. So data were collected prospectively for at months, beginning after completion of the first at control group, clinic appointments, 6 months post-randomization. So that to me sounds like a method as well. I don't know about you. I think the model was right there. Data were collected. This is what happened, what you did. It wasn't the result. Let's go into another one. So the target was method, the prediction was results. This is again line number 10 out of 12. So this is some context here, right? Is that why would you put a result at line 3? That was the target. So the target here is methods and the prediction was results. Again, the line number is 10 out of 12. So no pain was reported in the saffron group, whereas the indomethacin group experienced pain before X hours. To me, that sounds like a result. What do you think? This is a very valuable insight into our data here. We're using the model to explore where potential mislabeled examples exist. So again, the target was methods, the prediction was results, the probability was XYZ, pretty high again. Line number 11, really close to the end. Statistical significance was defined as P greater than. Well, that seems like a result too. Target, or P less than number. Target was methods, prediction was conclusion. The probability is really high. Now, again, line number 11 out of 11. Why would a method, the target label, be at the last line of an abstract? This is beautiful. I love this kind of inspection. This study provides class 2 evidence that regular aerobic training with or without post-exercise protein carbohydrate supplementation improves fitness and workload in patients with FSHD. The target was method. So that's, to me, an incorrectly labeled data sample. So you're now starting to see how we could use our model to improve our data set. Again, the target was conclusions. The prediction was results. PDT was associated with a significant increase in bleeding scores, P equals at, as well as inflammatory exudation. Maybe. We could keep going with these for a while. Target methods, prediction was results, but this is giving us some insights into what our model's thinking. Here's another one that's very strange. The target was results, but again, the line number is 4 out of 13. The prediction was methods. Baseline measures included sociodemographics, standardization, standardized anthropometrics, asthma control test, ACT, GERD symptom assessment scale, Pittsburgh sleep quality index, and Berlin questionnaire for sleep apnea. To me, that sounds like a method. That doesn't sound like a result. So I would side with the model here for a lot of these. Largest stream ever? What do you mean, Ashik? This is very interesting. So this is the power of at the end of when you've built a fairly good model, you want to explore the predictions where your model is wrong, but the prediction probability is very high. Because if your model has learned something significant, you'll find examples like these. So these are the most wrong samples. So as in, prediction probability is very high, but the model the model predicted wrong. So this is how you improve your data set. So if we were to go back through and go, you know what, there's a lot of samples that are like these. Let's go through and fix the labels, and then we'll retrain a model. And then you're building this loop, which is often referred to as active learning. So let's go here. Active learning, machine learning. Do we have a photo? Oh, this looks good. Can you see that? You should be able to see that. Okay, so we have data coming in. Deploy machine learning model, yes. Predict. Active learning. Select unlabeled items that are interesting for humans to look at. So we could select the interesting items for us is the ones where the model has predicted wrong with a very high prediction probability. Then we could re-annotate them, feed them back into the training data, train another machine learning model, and deploy it. And then all of a sudden we get this wheel effect. That's what we're after, the flywheel. I made this in on my GitHub. If we go to, where's my CS deployment tutorial? So if we go to, where's the PDF? Here we go. So this is the ultimate goal of machine learning, this is a lecture I gave the other day for Stanford, by the way. Tesla's data flywheel. So Tesla have a data source. They find something wrong with their data, or their car performs poorly on a data set, and they want to figure out where that car performed poorly. And then they find out that if you can see that, that's in the middle of a tunnel. Don't know if you can see that. But that's a tunnel, right? You can find this on that video. Tesla Autonomy Day is called the video. But they find that their model's performing very bad in tunnels. And then they find more samples of the tunnel, and they feed it back to the data set and train the model again. Notice how the model didn't really get changed here. They've just iterated on the data set. You could keep this model the same and then just continually, if the model's performing fairly well, you could just then continually improve on your data set. That's where I want to get. This is going to be probably one of my next big projects, is I'll build a fairly good model just to work. I know this model will work on data if the data is good. That's what I'm going to do. And then I'm going to spend most of my time figuring out how to iterate on a data set. I think that'll be fairly fun. So where were we? Make example predictions. So now here's the fun part, is that if we take a string, an example, how about we just try it on the demo papers we've been looking at? Let's can all of these. Look at this, right? So we'll take this. Now we want to prettyify this abstract. Look, there's a lot of crap going on here. I can't read all of that. It's too much. I want to break it down into something like this. Okay? Can we do that? Can we build a machine learning model to break it down into something like this? Let's see. I'll get this source. So we'll go here. Example. And now this is a nutrition study. I like nutrition psychiatry, the present state of the evidence. So does what you eat affect how you think? Mental illness, including depression, anxiety, and bipolar, etc., etc. If you're eating shit food, you'll probably think like shit. So we want to go abstract string equals, and let's just copy this. Again, this is very hacky, but you could imagine, as we discussed before, oh, I want to go forward. If we built a model that could work in a browser, so we could just convert our model from Python to TensorFlow JS, but we can inspect this, find the abstract, there we go, div class abstract, and we find this text. So our Google Chrome extension could work on this text and then break it into something like this. But for now, we're doing it in a notebook, but that would be the end goal. We want to process it with Spacey to turn it into lines of text. If you're not sure what Spacey is one of the most powerful NLP libraries there is. It's actually amazing. Spacey 3.0. Look at that. I'm going to actually watch this video later.
Hi, I'm Ines.
This is very new. So I'm going to like that already. Spacey is an outstanding library for natural language processing. But this is what we're using. So we're using Spacey. What this does is we set up an English sentence parser. We create a pipeline to parse. What I mean by this parse, I'm saying parse like P-A-R-S-E. My Australian accent might turn it into parse. But I want to parse this string. So, okay, yes, we get this string, but our model only works on, our model can't just work directly on this string. We need to pre-process it. We need to break it into sentences. We need to count how many sentences there are. We need to count the number of where each sentence appears. So that's the input to our model. This is sentence 1, so that'll get a number 0, and how many sentences total are in there. So Spacey has some great functions to do this for us. So we've just pasted in this entire big string here, really long string. We just took that whole abstract as one string. And now sententizer, we turn it into a list of individual strings. So Spacey did a great job at breaking this down into, there we go. So now instead of one string, it's a list of strings. So thank you for that, Spacey. Now we can write some little code to turn our string into a list of dictionaries. Why do we do this? So now we extract some structured data from our string. We've got line number 0, text, mental illness, total lines 9. Wonderful, right? And then we have line number 1, text, total lines 9, line number 2, 0 indexed, of course. So now we're starting to get close to where we can use this for our model. We'll one-hot encode it. One-hot encode it as well. Split it into characters because our model is trained on both tokens and characters. Then we'll make a prediction. So we probably want to turn this into a data set as well, but that's okay. So what order does it predict? 0, 0, 0, 2, 1, 1, 1, 1, 1. So what does this look like? Background, 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 methods, conclusions, conclusions. And if we break this down, boom. Have a look at this. So we've just taken an abstract. Look at this. This disgusting big paragraph of text. We've built a model to break it down into something like this. Background, methods, results, conclusions. Oh. Look at that. Background, methods, conclusions. Right? So, does this make sense? Mental illness. We need to make this bigger. Background. Treatment is presently dominated by pharmacotherapy, such as antidepressants and psychotherapy. such as cognitive behavioral therapy. However, such treatments avert less than half the disease burden, suggesting that additional strategies are needed to prevent and treat mental disorders. Yes. This review provides an overview of the nutritional psychiatric field. That's a method. Conclusions. It includes a discussion of the neurobiological methods likely modulated by diet, the use of dietary naturoceutical interventions in mental disorders and recommendations for further research. Potential biological pathways related to mental disorders include inflammation, oxidative stress, the gut microbiome, epigenetic modifications, and neuroplasticity. Consistent epidemiological evidence, particularly for depression, suggests an association between measures of diet quality. Okay, so to me, that's pretty cool, right? So we just took an abstract from the wild, right? And we passed it, and we turned it into basically something that could look like this. Now, again, we could format it a little bit better to say that the background is these 3 sentences, the method is this sentence, and the conclusion is this sentence. Is it perfect? Probably not. But we've only trained on 10% of the data that we have to build this model. And it's working pretty darn well. So how about we find another one? So an integrative review of sleep for nutrition professionals. Abstract. Is this an RCT? It's not an RCT. So we need an RCT because our data is trained on randomized controlled trials. So maternal versus paternal nutrition in critically ill patients, an updated systematic review. Have we got RTCs here? I think that is already there. Oh, I got an idea. Let's compare this one to the wild. Yes. We'll copy this into here. And we'll turn this into one string. Limitations. So we don't have limitations in our data set, but that's okay. Here we go. Example abstract. And this comes from here with removed formatting. So let's see how much our model agrees with this abstract. Okay, so fairly long. Oh my God. Look at this, ladies and gentlemen. Look at this. Objective. Okay. Well, you could say that's not really an objective. So that's wrong. That's all right. Postpartum depression is the most prevalent mood disorder associated with childbirth. Background. So now it gets these two right. Background. Methods. We search for meta-analyses of randomized controlled trials of nutrition interventions. Yes. Results. It gets all the results correct except for this one. Diet. Two Australian RCTs with dietary advice interventions in pregnancy had a positive and null. Okay, so it gets that wrong. And then conclusions. Oh, and it also classifies limitations as a result. With the exception of fish oil, few RCTs with nutritional interventions during pregnancy assess PPD. So you could say that's a result as well, but they've labeled it as a limitation here. Our data set doesn't have limitations labels. But then conclusions, it gets them right too. Further research is needed to determine whether nutritional intervention strategies during pregnancy can protect against symptoms of PPD. Given the prevalence, so boom, skimlit, we almost perfectly replicated an example from the internet. We took away the formatting and then skimlet brought it back in. And once again, we've only trained on 10% of the data that we have, so we could really step this model up. So I think that's enough for this stream. That was kind of how to build a machine learning model that builds a potential use case for the wild. Imagine you're a researcher, that would bring some value to you. If the abstract is, you could have an extension, a Chrome extension that reads the abstract, and if it's over 10 lines or something like that and they're not formatted, it could automatically break them down into being something like this. So I think that's a pretty cool project. Stay tuned for the next stream. We'll go back and make sure that all the code in here is optimized, and then, yeah, we'll go from there. But thank you so much for tuning in. This was Skimlit. Let me upload this to Google Colab. I'm going to put a note here. This way you can see it. Oh, sorry, GitHub. This way you can see it. Note. This project is still a work in progress. That being said, you should be able to run most of the code. So let's, I'll save this as draft 1. And then this can be renamed to Skimlit Milestone Project 2. Multimodal models, natural language processing, replicating papers, everything. This notebook has it all. So I'm going to save a copy in GitHub. If you want to see all the code for this, go and get it here. Add Skimlit v1. So you should be able to find this now. On GitHub. So go and check this out. If you want to run through this, let me know. If you try it out, if you find any errors, let me know. But otherwise, it's available on the GitHub now. And tomorrow I'm going to be coming back and fixing up, making sure everything runs smoothly, fixing up all the data sources and whatnot. And then, yeah, we'll see what else we need to do later on. But keep learning, keep coding, keep moving. I'll see you next time. Thank you all for tuning in.